Hello everyone, I'm G. Sagastan from the Database Exploration Lab at the University of Texas at Arlington, along with Suraj and Professor Gautam Das. This work was done in close collaboration with Muhammad and Professor Sanjudeep Basu Roy from the Big Data Analytics Lab at New Jersey Institute of Technology. The title for the talk is A Generalized Approach for Reducing Expensive Distance Calls for a Broad Class of Proximity Problems. Here we try to give you a very brief and broad overview of the proximity problems. Proximity problems is a class of problems which involve estimation of distances between objects to organize these objects based on their closeness or fartherness. One of the key aspects of these proximity problems is their notion of distances. So here we try to establish this notion of distances through some real-life objects and their relationship with other objects. To explain a little bit further, let us take some real-life examples of some cats, dogs, and toy balloons. So here you can see these two cats look a lot alike. So the distances between them is very minimal, like 0 maybe. And the dogs, even though they are from the same species, they are two different breeds. So basically their distance is like somewhat closer, but not exactly as close as the cats. But the distances from these cats and dogs to these toys are extremely high, and then they tend towards a large value, like for example 1. In fact, in real life, actually you can replace these cats and dogs with almost any real life object. For example, in the case of documents, you can establish the distances between documents and classify these documents based on their similarities. Now that we have established the notion of distances, let's get back to the proximity problems once again. In real life, you can see the big internet giants who try to solve this problem on a day-to-day basis. For example, like Google, Microsoft, DuckDuckGo, Startpage.com, and Swisscows. They all try to get documents which are as closer to the query word which is presented to them, which is a perfect example for a proximity problem. These applications are not just limited to documents. They span across a wide range of possibilities of applications. For example, maps. There are applications such as finding the minimum spanning tree on a map, finding a tour of a given set of POIs separated by roads. For all of these applications, they use the APIs like Google Maps API or the Bing API or the Waze API for the address resolution. Another example is the reverse images, where the task is to find out images or set of images which is as closer to the query image which is presented to the query engine like Google, Bing, and Yahoo. Along these lines, it finds numerous applications in medical field such as comparison of fMRI scans, comparison of CAT scans for the disease diagnostics. Having established the importance of proximity problems in real life, now we want to establish how expensive is the distance oracle costs in real life, which are the key component of the proximity solutions. Let's take the example of Google Maps here. So here you can see that for every 1,000 requests, you will have to pay a $2 fee. Imagine you are a third-party application developer, then you will have to incur all these costs for developing your services on top of it. This expensive set of distance computations which are used in solving the proximity problems help us to define the notion of oracles. Oracles are entities which, when presented with a pair of objects, gives the exact distance between these pairs of objects in real life. These are expensive. Consequently, computing all pairs distances is impractical. Added with the challenge of scalability, it is impractical to ask oracles for every pair of distances. The overall aim in this project is to reduce the number of the expensive distance oracle call at the expense of local computation for solving the proximity problems. For this purpose, we closely analyzed the proximity problems, identified the steps which involves distance calls, and then we realize that all of these distance calls are embedded in the if statements, which makes a decision about the particular problem. For example, if it is a k nearest neighbor problem, they wanted to now know if there is any distance which are closer than the identified k neighbors so far. Similar is the case for other proximity algorithms too, such as minimum spanning tree, wherein the distance computers are extensively used in order to decide whether a particular edge from the candidate set actually forms the part of the tree. Similar is the case for clustering algorithms, where the objective is to tightly pack similar objects, wherein the distance between the clusters are maximized and the distance within the cluster are sort of minimized. In all these proximity problems, we can see that there are if statements which consumes the expensive distance oracle calls. Now, we wanted to overlook or try to avoid some of these lookups in order to save distance computations without actually compromising the results of the proximity problems. Before we dive deep into the solution portfolios, we wanted to establish one more fact, which is the metric size properties. So given two objects, like you can see two hats on the top. So these two hats are same. The metric property says if the objects are same, the distance is going to be 0. In the second part of the image, you can see two hats and a rabbit. And you know that the distance between two hats are really small. And distance between one of the hat and the rabbit, if it is bigger, then the distance between the other hat and the rabbit is going to be bigger. Here we introduce the novel formulation of the problem in the light of system of linear equations, and we title it as direct feasibility test. Here we represent each of the distances in the entire object set as variables. Let's say you have two objects x and y and the distance between them is 0.6. Now we introduce a new variable x, xy, and we put that in the equation as xy minus 0.6 less than or equal to 0, xy minus 0.6 greater than or equal to 0. If you do not know the distance between two objects, let's say objects a and b, you introduce a variable xab, and then you introduce the weight in the equations like xab minus 1 less than or equal to 0, xab greater than or equal to 0. After which you formulate triangle inequalities to be added to these variables. So imagine you have a triangle xyc, xy minus xyc minus xzx is less than or equal to 0, and you add all the triangle inequalities similar to this for this triangle, and then you add it for all the triangles which are there in the system. You form a system of linear equations. You solve this linear equation using an off-the-shelf linear programming solver, and you check for the feasibility region, and if you do not have any feasibility region, you basically avoid computing the distances, and then you skip over the if statements because there is no feasible region to it. The direct feasibility test through the reauthoring of the if statement is a very novel formulation of the proximity search problem, which was not studied previously. This introduces a system of linear equations. The equations for variables is in the order of n square, and the equations for triangle inequalities is in the order of n cube. Off-the-shelf linear inequality solvers are expensive, so computational of answers for this direct feasibility test and finding regions in order to save distances is only applicable to small graphs, and it is not scalable even to medium or small size graphs. Since the direct feasibility does not scale beyond small data sets, we started looking at more practical approach for scaling up, which is the graph theoretic approach. In this particular modeling, all the objects are the nodes in the graph, and all the distances between the objects are the edges in the graph. As you can see from the suite of cards, there are certain edges which are resolved, which you can see in green are the known distances, and there are some red edges which are the distances which are unknown. So earlier in the discussion, we have mentioned that if statements are main reasons why distance computation calls go up. So we start asking ourselves this question: can we reauthor these if statements to avoid the expensive distance call as much as possible and whenever it is possible? Thus, we modified the if statements to the one which is on the right hand side. So if instead of writing if the distances of OI OJ is greater than or equal to distance of OK OL, we rewrote them as if LB of distance OI OJ is greater than or equal to upper bound of the distance OK OL, then you do not have to do any distance computation. You can skip over. If you do not find this condition satisfied, then you actually go and find the distance between these two pairs of objects and try to continue the flow of the algorithm. Here is the exactness genie. The genie says we produce the answers which are the exact same of the answers just produced by the algorithms without our modification or reauthoring, which means the length of the minimum spanning tree that we obtain is exactly the same as that of the vanilla prims, the exact same clusters and exact same intra-cluster distances for clustering, exact same k-nearest neighbors for k-nearest neighbor problems. Thus we have transformed the problem of reducing the number of distance constant proximity problems into finding exact upper and lower bounds for unknown edges. Computing the low upper bound for the unknown edges is rather straightforward. It's the length of the shortest path. However, for the lower bound, it is far more trickier and more harder. For example, let's take the example of one unknown edge xy, which you can see at the both ends marked in red, and then you have an edge which is in the middle, which is connecting two blue dots, which is OI and OJ, and you know the shortest path from X to OI, and you know the shortest path from OJ to Y. The length of the lower bound is actually the remainder after you fold the shortest path onto that particular edge. Here you can see X is being folded onto OI and OJ, and shortest path from OJ to Y is folded onto the edge YOJ, and the remainder is the lower bound. And then you will have to calculate these values for each of the known edges in the graph in order to find the best lower bound. Thus we formulate two main problems that we're going to tackle in this work, and the query and the update model problems. The first problem is, in response to a query of an unknown edge, how to obtain the lower and the upper bounds exactly. And if any of the edges is resolved, it's the second problem, how to update the data structures to get the latest upper and lower bounds on the next queries. There's an already existing dynamic programming approach which is given by Wong and Sasha, which is a cubic algorithm, but we would like to see the possibilities of improving these complexities. Now we introduce a solution framework which was inspired by the Dijkstra's shortest path algorithm. We titled it as shortest path lower upper bound algorithm. Imagine you have two contact cards between which you do not know the distance. So what exactly you will do in the algorithm is you will try to find out the shortest path from the contact cards, which are both ends of the contact cards, to each of the objects in the universe. Now you find the shortest path between these two images, and that is your upper bound. Computing the lower bounds is a much harder problem, as we have explained previously. Now we take a much simpler approach towards finding the solution. So since you do not know the distance between these two contact cards on the right, with the right flap on the top, what you do is you take every known edge in the graph, let's say two contact card with the left flap on, you compute the shortest path from both ends of the known edge into the endpoints of the unknown edge, and then you calculate the lower bound as follows: the edge minus the path lengths from both endpoints, and then you do it for each of the known edges in the graph, and then you declare the answer as the one which is the maximum of all the lower bounds. The time complexity of this algorithm is exactly the same of the Dijkstra's algorithm, as it is evident from the algorithm itself. This scales very well to the medium to large size graphs. It finds the exact answers as that of the cubic algorithm which was proposed by Sasha and Wong, but this does not scale to very, very large graph settings. Now we have a linear programming based solution framework for small graphs and a shortest path based solution frameworks for medium and large size graph. But for the large graph and very large settings, we do not have a solution framework. Thus we started trading off the accuracy of the lower and upper bounds for the scalability part. Even though these algorithms produce looser bounds, with the lower upper bounds may be larger, the lower bounds may be smaller, we have unlocked the power to solve very large graph settings. Here comes the exactness alert once again for the approximate lower bound and upper bound. We relaxed the tightness of the bounds, but we still do not compromise on the quality of the results that the approximity algorithms produce. We are producing the exact same answers as the proximity algorithm was generally produced at the expense of extra oracle calls, which are marginal. To design algorithms which are scalable for very large graph settings, we would like to remind the users about the shortest path based solutions that we have discussed previously. So here you can see two shortest paths, which are from the known edges in the graph to the unknown edges, which is another question. So we simply replace them with triangles which forms direct edges with these unknown edges. Thus the lower bound computation is far more easier as the difference between these two edges. We use an adjacency list representation of the graph for efficient query answering. For further optimizations, here you can see the acorn, the distance from the acorn to the knitting kit is given and to the aeroplane is given. In the second row, you can see the distance from the knitting kit to the contact card is given. So you can use this as a starting point for you to find out these kinds of triangles. So we apply numerous optimizations on this technique in order to scale for the large settings. One of the main optimizations that we use is to find intersections between these two rows. You can see that if you want to find a triangle, all you have to do is to find these common intersections here. Acorn distances to knitting kit is known, contact card to knitting distance is known. So if you wanted to find out a triangle for an unknown edge contact card and the acorn, all you have to do is to make this triangle, which is similar for aeroplane to acorn and contact card to acorn. Now BST comes to our savior here. So what we do is we try to store these distances as a binary search tree. So instead of you have to go through every entry in the list in order to compare, all you have to do is to search in the binary search tree. So here acorn distance to the knitting kit, aeroplane, and the contact cards are given. So we try to organize them as a binary search tree as an optimization which speeds up the computation really fast. As a main theoretical results in our paper, we have proved that the average time for time scheme for looking up an edge is in the order of m by n. Here you can see the glimpse of the dataset that we have used in our experiments. The SFPO dataset with 21,000 objects, Flickr dataset with 10k objects, and UrbanGB with 360,000 objects. All of these are real-life datasets. On the second column, you can actually see the algorithms that we have used, the proximity algorithm that we have used to validate these algorithms, and you can see the generality of our solution framework to a wide range of proximity problems. Here are the state-of-the-art competitive algorithms to the methods that we have developed. ADM is the cubic algorithm that we have mentioned previously, and it gives you the exact answers. LESA and TLESA are for the very large graph settings. Now I would like to give you the glimpse of the results portfolio. Results portfolio, you can see the lower bounds produced by the ADM and SPLUB are exactly the same, which is the same case for the upper bounds. The tri-scheme lower bound, which is the approximate lower bound, is much better than the TLESA lower bounds and the LESA lower bounds, as you can see from these pictures. Let us take a quick look at the answers for the PRIMS algorithm. So you can see that the ADM takes a very large amount of time, and SPLUB takes a fraction of the time that is required by the ADM, and tri-scheme is blazingly fast. You can don't even see in these graphs. Here is the glimpse of the distance save that we obtained using PRIMS algorithm. Here you can see multiple fields. We would like you to take a look at only the two fields which are given the last four columns, the LESA, the save, the TLESA, and the save. So you can see that as the scale increases, your distance save ups go up, and it is incredibly doing very well against LESA and TLESA in the order of 60 to 51%, and even the 63% is in the order of millions of distance calls. There are more details in the paper from various proximity algorithms, the drawbacks of the proximity competitive algorithms, proof of concept as a result from direct feasibility test, scalability experiments, computational overheads, response to varying parameters in PRIMS algorithm. Please take a look at our work for more details. Thank you.